Alright, so in this video we're going to be talking about the final K value that we need to discuss. So remember, K values, or K is going to be the equilibrium constant. So KSP is going to be the equilibrium constant of solubility. So it relates to how soluble an ionic compound is when you place it into water. So if I have AgCl versus KCl, well, I know that KCl has group 1, so it's very soluble. So if I put it into water, it makes the ions, and it makes lots of these ions because it's very soluble. So I know that my K value for this process should be very large because it's product driven. I have more ions in the solution than I do of the solid. So when I take silver chloride is not soluble. When it dissolves, it would make this. It would make the silver ions and the chloride ions. Well, for this process, because silver chloride is considered to be insoluble, the K value is very small. That means that there is lots of your reactants versus your products. It's very reactant driven. So KSP is going to be the equilibrium constant when you dissolve an ionic compound into water. Okay, so solubility. The only real solubility rule that you need to know is that group 1 salts are going to be soluble. So anything with like potassium, rubidium, sodium, anything with nitrate will be soluble, and anything with ammonium will be soluble. So anything with any of those ions will be considered to be soluble. So in that case, KSP should be greater than 1. It should make lots of ions when you put it into water. Ionic compounds that are not considered soluble do dissolve to a very, very small extent. So basically anything that's insoluble, you can get it to dissolve. You can't get a lot of it to dissolve, but you can get it to dissolve. So these salts are going to have a very small K value. So KSP is their equilibrium constant when we dissolve a salt into water. If KSP is large, if it's larger than 1, it's soluble. If it's less than 1, it's not considered to be soluble. But everything dissolves though. So if I have silver chloride and I dissolve it, I'm going to make my silver ion, and I'm also going to make my chloride ion. Well, KSP, okay, K is the equilibrium constant. KSP is the specific equilibrium constant. So anytime that we are looking at the equilibrium constant, remember that's the ratio of products to reactants. So this one would be equal to our products, so silver ions to the power of its coefficient multiplied by chloride ions to the power of its coefficient, which is just 1 to 1 here, and then divided by our reactants. But if you remember, solids are not included in the equilibrium expression. So technically there is no bottom for KSP. It's just going to be something times something else, sometimes to certain powers. So don't include solids anytime that we have a K expression. So the smaller the KSP, the smaller the number of ions you have, because you're going to have less products for that particular process. Okay, so molar solubility is equal to the number of moles of a solute in 1 liter of a saturated solution. So saturated, remember, that's the amount that you can get to dissolve in 1 liter of water. So solubility can also be expressed in grams per liter. So just make sure you watch your units when you do these kind of calculations. A saturated solution is going to be one where you can't dissolve anymore. So even if you try to dump more of that solute in there, it won't dissolve. So you'll just see solid like settle at the bottom. That's like when you have sweet tea and you are trying to dump more and more sugar in there, and then it just goes to the bottom. It doesn't dissolve anymore because you've hit saturation. All right, so let's look at a problem. At a certain temperature, the molar solubility of salt, and it's giving the charges, so Mx, so this salt, is found to be 4.15 times 10 to the negative 6. Calculate the KSP value. Okay, so when we're talking about solubility, we're talking about taking that salt, that solid salt, and dissolving it. And then it should break apart into its ions. So here are our ions. All right, so here's our chemical reaction, our equation, and we know that we're looking for KSP. Well, KSP is equal to products over reactants, so that would be M to the first and X to the first. And then we don't put this in there because it is a solid. So what we need to know how much of these items we have in the solution at equilibrium. So we're going to make an ice table. And for this particular process, since it's solid, we don't care about it because it's not included in the K expression. So initially, there are no ions. The change, well, after I dissolve it, I'm going to put so much of this in there and so much of this in there. And then remember to include the coefficients. So this is to the 1x, this is also to the 1x. That becomes important because sometimes it's not 1. So this is x and this is x. Well, it tells me that the molar solubility is 4.15 times 10 to the negative 6 moles per liter. Essentially, what that means is when I dissolve this, I am going to have 4.15 times 10 to the negative 6 moles for every 1 liter of solution dissolve. Well, everything in here is a 1-to-1 ratio. That means that if I dissolve 4.15 times 10 to the negative 6 moles of this, I should create 4.15 times 10 to the negative 6 of that and that. So little x is just going to be the molar solubility because it's a 1-to-1 ratio. Okay, so to get KSP, now I can just plug it in. KSP is equal to 4.15 times 10 to the negative 6 to the first multiplied by 4.15 times 10 to the negative 6 to the first. So when I solve for that, I'm going to get 1.72 times 10 to the negative 11th. And remember, there are no units for K. All right, so let's calculate the KSP from solubility expressed in grams per liter. So at a certain temperature, the solubility of calcium sulfate is found to be 0.66 grams per liter. Calculate KSP. So we are looking for KSP of calcium sulfate. So when calcium sulfate dissolves, it makes the calcium ion. It also makes a sulfate ion. So KSP is equal to the concentration of the calcium ion multiplied by the concentration of the sulfate ion, both to the first, since our coefficient is 1. And then we do not care about this. We don't put that in the K expression because it's a solid. So what are we going to do? We're going to do an ice table because I need to know at equilibrium how much do we have of those. Okay, so again, I don't care about that. And then also initially, this is going to be 0. This is going to be 0. And then this goes up by 1x. This also goes up by 1x. Some number, it goes up by some number. So now we have x and x, but I've got my solubility is 0.66 grams per liter. So that means for every 1 liter of water, I will dissolve 0.66 grams of my calcium sulfate. Well, I need to know how many moles that is. So I need to convert first. So now, the liters is fine. I need to get rid of the grams. I need moles on top. 1 mole is equal to 136. So that comes from the molar mass, calcium sulfate. So that's mass of 1 calcium, mass of 1 sulfur, and 4 oxygens. So that will give me 0.0048 moles per liter. So my solubility is 0.0048 moles per liter. So for every 1 liter of water, I will dissolve 0.00482 moles. So it's a 1-to-1 ratio. So that means it's going to be 0.0048, which is also equal to this. So now we've got our solubility. We can plug it into the K expression. So it's 0.0048 to the first times 0.0048 to the first. And that's equal to 2.353 times 10 to the negative fifth. All right, so let's look at a slightly different problem. All right, so let's calculate the KSP of a salt, XOH2. The molar solubility is this. Okay, so we're looking for the KSP value of this salt. So when this dissolves into water, I'm going to get one of those, so that's going to be a positive 2 charge, and then 2 hydroxides. That's the difference here. There is a coefficient that is not 1 in this case, so it makes it a little bit trickier. You have to really pay attention to what you're doing here. So my KSP will be equal to my products. So my X to the first, but this one will be to the second. Oops. So you have to square that value. All right, so now we're going to do an ice table. Again, I don't care about this. This is 0, this is 0. We're going to add x, but this is 2x. All right, so this will go up by some number, and then this will go up by twice that number because there's 2 hydroxides for every one of these that we have. So now the molar solubility of this compound is this. So for every one of these, I will dissolve 2.0 times 10 to the negative 6 moles. All right, so for every one of these, I make one of these. So x should be equal to 2.0 times 10 to the negative 6. Well, if I know what x is, then I can figure out what 2x is, because it should be twice the amount because I make 2 times the amount of hydroxide. So it's 2 times little x, which is that. So that should be 4 times 10 to the negative 6. All right, so now I've got my equilibrium values. I can go back and plug it into the K expression. So this is 2.0 times 10 to the negative 6 to the first, and this is 4.0 times 10 to the negative 6 squared. And so many people will forget to do that part. So this part and this part, a lot of people will forget this. That's why every single time you do an equilibrium problem, even if it is a 1-to-1 ratio, just go ahead and write that coefficient down. Write that K expression down. Make sure you put those things there so that they're in place. So when you do the calculation, you remember something is squared, something is multiplied by 2, okay? So now, when I calculate this K value, I will get 3.2 times 10 to the negative 17th. All those things are very important. It's so easy to miss it. Okay, so calculate the molar solubility in grams per liter from KSP. Given that the KSP of silver sulfate is 1.41 times 10 to the negative 5th, calculate the solubility in grams per liter and molar solubility and moles per liter of the silver sulfate. So in this one, we're going in the opposite direction. So we're still talking about the same process though. We're talking about this, dissolving. So we're going to make 2 silver ions here, and then we're going to make 1 sulfate ion. So our K expression should be equal to silver to the second multiplied by sulfate to the first. Okay, so now we need the amounts at equilibrium in order to do this. We have the KSP value. So we're looking to get those values right here. I want to get the molar solubility. So how much of this will dissolve in water? 1 liter of water, how many moles of that? So still the same process. We're going to still put together a nice table. So this will be 0, this will be 0. This will be plus 2x, this will be plus x. So we are trying to find little x here. So we're trying to figure out how many moles will dissolve in 1 liter. And I know that the KSP value is 1.41 times 10 to the negative 5th. So what we're doing is we're going to solve for little x. So my K value is this. My K value is this. And I know that silver is 2x squared. And sulfate is x. So when I do the math here, it's going to be 1.41 times 10 to the negative 5th is equal to 4x squared times x. Well, that's the same thing as 4x cubed. Now you solve 4x cubed is equal to 1.41 times 10 to the negative 5th. So you're going to divide both sides by 4. That divided by 4. Okay, now we're going to have x cubed is equal to 3.525 times 10 to the negative 6. Okay, so now to get rid of the cubed, take it to the 1/3. So take this to the 1/3 power. That gets rid of the cube root, or the cube. And you're going to get 0.0152 moles per liter. And that's going to be your molar solubility. So now if I need to take it a step further and get my value in grams per liter, I just need to convert it. So you just do the opposite. You have moles over liters. Moles on the bottom, grams on the top. 1 mole is equal to all right, so grams per liter will be 4.7, 1.2 grams per liter. All right, so basically when you're setting these up, please, please, please make sure you pay attention to the coefficients because that's really the trickiest part.